It's fine, yeah. Good afternoon, everyone. I am Ioanna Papanikolaou. I'm a second-year PhD student here at the Future Infrastructure and Built Environment Center for doctoral training. I also work for Costain as an engineer on Thames Tideway. So today I will present to you my PhD work so far, which is Graphene-Reinforced Cement Composites for Self-Sensing Infrastructure, and I'm supervised by Professor Abir Al-Taba. Also, part of this work was done in collaboration with Heidelberg Cement, who is represented here today by Mr. Marco Goisis, who is one of the co-authors of the paper. So just to give you a background around the need for smart biomimetic materials, basically half of the construction budget across the European Union is spent on repair and maintenance. So rather than using our limited pot of money for new infrastructure, we're using it to actually repair and maintain the infrastructure that we already have. And especially in concrete structures, what is even worse is that these repairs are very ineffective. So within 10 years, at least half of the repairs will fail, and then you need to go out and repair again. And of course, this has a lot of sustainability implications, especially around social implications, disturbing the public, lack of reliability of our infrastructure. Also environmental, we've heard that concrete is one of the most damaging materials, construction materials, and of course economic, due to budget constraints. So over the last year, scientists have looked to develop what we call biomimetic materials. These are basically materials that are inspired by nature. So they are inspired by all the living organisms. And we mean materials that can adapt and respond to their external environment. And in the context of construction materials, we mean materials that can self-sense their condition, they can self-diagnose the condition, and then repair in case they're damaged. And we have already seen some commercial success stories. For example, scientists have been inspired by organisms that glow in the dark to then develop pavement that glows in the dark in the same way. I work as part of a larger group of PhD researchers called Resilient Materials for Life. And this is a collaboration between the University of Cambridge, Bath, Cardiff, and Bradford, and we are funded by EPSRC. And the aim of the program is that by 2022, we will investigate biomimetic materials that can self-diagnose their condition, and then they can self-heal if they're damaged. And we're working across 4 different themes that you can see here. So one is physical cracking, chemical attack, aging, and also cyclic damage. So we are looking to develop materials not only that self-heal, but can also self-diagnose without the need for an external intervention. So I've mentioned self-sensing. What do I actually mean by self-sensing? You're all in this room very familiar with sensor technologies. However, some of the challenges with external sensors, that sensors are attached or embedded in the structure, is that often they're associated with very high costs to either install or to maintain across the life cycle of the project. Some of them also lead to very low sensitivity or incompatibility with the actual structure. And also, the sensors themselves sometimes are not very durable, so they might not last for 100 or 120 years that a structure is expected to last. And as Sakthi mentioned earlier, visual surveys are still the norm for pretty much every infrastructure owner. So they depend on an engineer actually going out once every 2 or 4 years to physically inspect if there's any cracking. But what we mean by self-sensing is that the structural material itself can monitor its condition without any external intervention. And the good thing about this is that the sensing material is the actual structural material. So it has natural compatibility with the structure, natural high sensitivity, and of course durability. So as an example, what I'm looking on is self-sensing concrete. So the concrete itself remains a structural material, but it also has the added-on functionality of sensing its own condition. And to generate that self-sensing aspect, I'm using the nanomaterial of graphene. So graphene was isolated back in 2004 by the exfoliation of graphite. And then the researchers that discovered graphene then won the Nobel Prize in Physics for their discovery. So graphene has some very unique properties. It is the thinnest possible material that you can find, but also at the same time it is the strongest known material on Earth, and it is estimated that it is roughly 200 times stronger than structural steel. It is extremely lightweight as well, which is another benefit for its use in structural composites. It has very high Young's modulus and flexibility along with fracture strength. And another useful property is that it has some barrier properties that we can explore for durability applications. And the property I'm looking to take advantage of is the electrical conductivity. So graphene is one of the best electrical conductors, so I can use that to generate the self-sensing mechanism. And it is important to point out at that stage that over the last 5 years at least, there have been a lot of papers on graphene in various composites, not only concrete but also steel and polymers. And when people say graphene, there are actually many different graphene materials. So graphene doesn't only mean one thing. We have this graphene, which is a graphene that was discovered back in 2004, and this is a single-layer graphene. We also have graphene oxide, which is the middle one. The graphene oxide has oxides and groups that then allow it to mix very well in water and hence concrete. We also have reduced graphene oxide, which again is another type of graphene. And unfortunately in the literature it's not always clear what type of graphene is used, how many layers it has, and all these properties actually affect the resultant properties of the composite at the end. And in terms of graphene cement composites, I'm using a multi-layer form of graphene, so not the very thin layer, one-layer graphene, because that would be prohibitingly expensive for anything in concrete. But I'm using something called graphene nanoplatelets, which have about 40 nanometers thickness. And there is some general agreement in the literature as to what is the effect of graphene nanoplatelets when they're added in cement mortar or cement paste. And in general, the fluidity of the mix decreases dramatically. I think all authors agree on that, because graphene is a nanomaterial and it is very difficult to mix. And also we have seen improvements in strength and then a consequent improvement very often in the durability parameters as well. And very importantly for me and my self-sensing is that the electrical conductivity increases significantly when you mix graphene in your concrete. However, the challenge in the literature is that authors use different percentages of graphene. They get different percentage improvements in strength. And also, even if people use 0.3 graphene, let's say, other people found 5% increase in strength, and other people found -10 increase in strength. So there is still not a definitive answer as to how much graphene you need to add in concrete and whether that graphene has a beneficial effect, especially in terms of strength. So, as I've mentioned earlier, one of the key challenges that I had so far in the literature is that the graphene materials are not always characterized, and it is very difficult to compare like for like in the papers. And the other challenge is that because graphene is a nanomaterial, it is extremely difficult to mix it uniformly in concrete. So I have two photos here from the lab. When you add graphene, by the way, I have graphene in powder form in this case. When you add graphene, it tends to agglomerate very quickly and it doesn't mix in water at all. And then you need some sort of chemical or mechanical treatment to make sure that it mixes homogeneously first before you add it in cement. So over the last 2 years of my PhD, I've tried loads of different mixing methods, loads of different chemicals and mechanical methods to find an okay method to disperse it homogeneously. And we've done a lot of work with that, with Heidelberg cement to understand that homogeneity when you mix. And then we've run an industry survey last year, and a lot of people in this room have answered, so thank you very much. And we try to understand what are the actual problems encountered with concrete structures and the current use of sensors, and whether graphene could help in solving some of these challenges. So we wanted to identify the high-value areas where we could make our graphene work for the industry. Just a bit, I've sent my survey to around 300 to 400 people in the industry. I've got 78 respondents back. Due to my contracting background, I guess over half are from contractors, so the results might be biased a bit from that. We had over 55% with 15 years experience, so, and most of them are UK based as well. So in terms of concrete performance issues, the biggest challenge, and maybe that comes from the contracting aspect, is the cracking due to poor workmanship was identified as one of the key challenges in terms of damaging concrete. Also cracking due to poor specification followed by water ingress and penetration. And what was interesting to see is that any cracking or any defect in concrete in most cases led to immediate repair of the structure. And then it was followed by enhanced monitoring of the structure. So actually, a lot of the infrastructure owners need to go out and repair immediately or improve their monitoring frequency. And when I then asked about these sensors, if they have identified any key challenges, the cost of installation of the sensor is very high, followed by the data interpretation. So what happens very frequently is that we install sensors, but then the actual engineers don't know how to interpret the data and they don't know the right time to intervene. Of course, lifetime and durability of the sensor was another concern, followed by reliability of the data. And it was encouraging to see that 15% found no challenges, so that's good. So when I then asked about what are the biggest opportunities, what do you want a graphene cement composite to do for you, you can see that the biggest priority, these two, were really an improvement in tensile and flexural strength, followed very closely by a self-sensing mechanism. So what I get from this graph is that the industry is not really interested in an improvement in compressive strength, because you can get strength improvements with most of the admixtures that you currently have. You can get it through a robust mix design. What people want to see is an improved functionality that you wouldn't have with a change in the mix design. And in terms of barriers, this keeps coming up in every single presentation. The cost of the material is the perceived main blocker of introducing graphene as a nanomaterial. Also, this is followed by the lack of industry standards. The industry is very conservative, so it is very hard to convince anyone to even take a trial on something like graphene in concrete yet. So the standardization bodies really need to drive the introduction of new materials. And again, lack of technical understanding, I guess, is expected as it is a very novel research area. I was very, very surprised to find that health and safety and environmental effects weren't really a concern for people. So just to be clear on the cost, graphene currently is very expensive. It is an expensive material to use, but it also depends a lot on the actual graphene type that you use. So if you use the ultra-thin graphene, this can cost over £1,000 per gram, and is used by companies like Samsung, Apple, to use in advanced electronics. If you use the graphene I use for concrete, it is much, much cheaper. It's roughly £200 to £300 per kilo, so we are talking about a completely different scale. Graphene is extremely dependent on the manufacturing process. So if you don't want the super pure graphene, then the cost comes down significantly, of course. And again, the number of layers and quality is a big thing. So in general, as you go down in the number of layers, the more expensive it becomes. And for us in infrastructure and concrete is a commodity material, so we really need to find the right balance between the quality of any material that we would use and the cost to the user. And again, graphene research is very new, so the cost is expected to come down significantly as the process is scaled up. And I know it didn't come up as a concern, but I think health, safety, and the environment is very important consideration. So here in the UK, the Health and Safety Executive has done a lot of work on the use of nanomaterials at work. And a lot of the admixtures that we currently use in concrete, they are comprised of nanomaterials. So I would urge you to familiarize with these because nanomaterials are everywhere, basically. And in terms of sustainability, we've run very recently the first ever life cycle assessment of using graphene in concrete. And what we actually found was that if you look from GGBS to the left, this is a standard concrete mix design. What we found was that our graphene product, which is this one, has really a tiny effect on the environmental sustainability of the whole mix design. And the biggest impact by far is the use of Portland cement. So if we could somehow reduce Portland cement whilst giving the same functionality to our concrete mix design, this is where our sustainability benefit would really be evident. So yes, this is a graphene product, minimum effect. The actual plasticizer has 3 times more effect compared to graphene. So that's my presentation. Thank you very much for listening, and of course to all the people that have been involved in my survey and supporting me over the last 2 years. I look forward to your questions.